All right, yeah, so that's, you heard the title. This is really going to be kind of an update on a CIDEC project called Coupling Approaches for Next Generation Architectures, or CANGA. So I'm really speaking on behalf of this entire team.
Hey, Phil,
so
can you full screen for us, please?
Yes.
Can you go full screen for us, please?
I think we tried that earlier. Okay, is that better?
Perfect, thank you.
All right. So as you all know, and it's been mentioned several times during this, we're in this sort of parallelism pandemic where performance is coming from increased parallelism, both kind of within nodes and within devices on nodes. So substantial parallelism all across the architecture. And then, as also been mentioned, some of these devices are kind of mutating. So we have not only CPUs and GPUs, but things like tensor cores, burst buffers, even configurable architectures like FPGAs and others. And we're starting to also see sort of custom architectures. PostGre is sort of one example, but DOE has a project looking at similar modifications for custom chips. So all of this, to make use of all of this, we're really needing to kind of expose sort of tens to hundreds of thousands of threads per node with variable workloads. So a number of treatments for that are sort of coming out. The directive-based approaches, OpenACC and OpenMP5, and those have sort of moderate community spread, particularly in Fortran. That's really the only sort of portable programming model out there, unless you go to a domain-specific language or something. On C++ side, you already heard Luca talk about Cocos, and that's particularly recently that's had sort of a larger community spread, I guess. So all of these are good. You know, we can get sort of on the order of between 3 and a few tens of factors of speed up if you look at sort of full application performance on a per node basis. But these programming models are only sort of treating some of the symptoms. They're focused on portability and sort of data layouts and loop level abstractions. But it doesn't solve kind of the fundamental problem we have in the Earth system modeling community, where we really don't have enough work, even at high resolution, to spread across or to provide that kind of parallelism on a node, especially when we're still getting the best throughputs and a strong scaling regime. So we're still struggling to get enough parallelism there. And that's why we're looking at things like superparameterization and LES models underneath. But I wanted to talk today a little bit more about asynchronous mini-task programming models, and this is what we're exploring in CANGA. So I've talked about this at previous meetings, but just to kind of review that this is where you consider your application as basically a federation of tasks, and those tasks are actually on sub-blocks of the domain, so you're still getting the domain decomposition plus some task decomposition. So the tasks have to have clear interfaces with no side effects so that the lightweight runtime can do the contact tracing in the sense of creating the dependency graph and scheduling the work. So the figure you see at right is kind of a complicated DAG from a combustion simulation. So there are a number of these task parallel programming models out there. I'm going to be focused a little more on kind of the Legion side because it's developed between Los Alamos and Stanford, but there are others. So on the computing side, this allows us to expose a lot more parallelism. You get some load balancing. You can also build in some fault tolerance, so if a task fails, you can relaunch. You can map tasks to appropriate hardware, so this is a way of kind of trying to get at the hybrid node problem. On the science side, it's kind of a way of managing complexity, so if you want to add or remove functionality, it's just a matter of adding or removing tasks or not registering tasks. but I think more importantly, we can start treating these coupled climate models as a collection of processes rather than these kind of large monolithic stovepipe components, right? So, so you can couple the tasks or the processes that need to be coupled at the appropriate time and space scales. But that requires some algorithmic change too, and I'll talk a little bit about that later. And then finally, we can include more of the overall sort of climate science workflow. So you can add things like in situ analysis and other aspects of the science workflow. Yeah, so this is part of the CANGA project. We actually have 3 parts. The first part is actually exploration of these task parallel models. But the other 2 parts are associated with algorithmic improvements for coupled modeling, including kind of remapping and time integration. So I'll breeze through those last 2 toward the end of the talk, but I'm going to be focused for this audience mostly on the first. So I mentioned we're primarily using Legion, although all of these task parallel programming models are a little bit complicated to use in a native fashion. So what we're using instead is a framework called Flexi, a flexible computer science interface. So this is another C++ application framework where they provide kind of more application-centered abstractions to the AMT runtimes underneath. So Flexi supports Legion HPX and Charm underneath. There's also kind of a reference MPI implementation, although that doesn't do the sort of task scheduling. That's kind of a manual MPI version. So to be able to use this Flexi framework, basically you develop what we call a specialization layer. There's actually a reference specialization layer as well. That's sort of a generic unstructured mesh, but to get better performance, it's good to just develop your own specialization layers. So we have one for the MPAS meshes, for example, where you can do the mesh and the partitioning. You can set up the index-based things for owned, shared, and Halo regions, and you can make it a little more performant that way. And then the Flexi supplies sort of the contract tracing interfaces. So you need to register a field with the framework and then register your tasks, which is essentially the task interface with each of the input and output fields, and you have to declare the intent of those so that the runtime can track the data flow through the model. And then you just launch these tasks on the distributed index space. So the code, when you code this up, actually can look pretty similar to your current application code. It's just the runtime doesn't see all of that. It just sees what you've registered and schedules things appropriately. So we currently have a prototype coupler built on this. It still uses the current sort of coupling paradigm where we have 4 large components, so we can sort of compare things directly. So we have the interfaces and the argument lists for all the functionality for the ocean, atmosphere, sea ice, land components, all the tools that we typically need, merging, remapping, and averaging. So all of that's currently working in Flexi. We can run several time steps and see the data flow going through. But right now, some of those functions are just simple functions at the moment, partly because the Flexi model was built for sort of single mesh applications. So we're still waiting for some of the multi-mesh functionality to show up. That's supposed to show up in the next month or 2 years. So once that's there, we can really add more realistic functions and add real or data components for the coupled system. But we've got enough there now so we can start sort of breaking up these interfaces and to see how much more parallelism we can expose through those layers. So that's sort of the top down, but we're also splitting up the large component models as well. So we have a version of the MPAS-O ocean model now working under this Flexi framework as well. So we did the usual thing, started with the transport and shallow water kind of test cases, but now we have enough functionality to do sort of baroclinic channel models and other things. We haven't done the barotropic split yet, so that still remains to be done. It does include all the parallel I/O capability that we need, and we're starting to also add in situ analysis. So in particular, computationally intensive ones like the Lagrangian particle tracking that we use in the ocean as a diagnostic that sort of mimics the kind of floats that are drifting around the ocean currently. So they're working on optimizations and predictive load balancing for that particular analysis member. And this is just a quick sort of the usual point and grunt proof that things are running. But you notice the data flow graph down on the bottom. You could expand all of this, but we're still not getting quite enough parallelism. We'll need to break this further apart to try to expose more task parallelism even within the dynamics. The dynamics is a little more of a challenge just because there are fewer opportunities for that task parallelism there, which brings me to the land surface model, which is another component we're looking at. And this is sort of a poster child for task parallelism. Land models are typically built up from a large number of various process models working on various vegetation types and land surface types. So it's really an ideal kind of application for a task parallel model. So we've been extracting kernels from the E3SM land model, porting them to C++, and then we developed a lightweight interface layer on top of those that actually supports kind of Legion and Plexi, but it also supports Cocos. So we're kind of hedging our bets there, and we're able to support a number of different programming models there. And this is the usual scaling curve. This doesn't include the Legion. It wasn't quite working yet when we made this slide. So, but you can see the usual kind of Cocos CUDA implementation gives us, you know, a few factors of 10 over CPU implementations. And then there's a paper that describes this that showed up in supercomputing last year, I believe. Okay, so just to summarize this section before I get into the algorithmic work, we've made a lot of progress on this. We're getting to the point where things are relatively realistic, and by this time next year, if this meeting happens, we should be able to evaluate sort of the performance and ease of use of these particular programming models for real applications. I suspect we're going to find in the end we need a mix of programming models at various levels in this hierarchy. So there will be task parallelism at some levels, and we're still going to need the sort of loop level abstractions as well from other programming models underneath. Okay, so I'm going to switch gears now and talk a little bit about some of the algorithmic change we need to make some of these things happen and to improve kind of coupled climate models in general. So one set are the RNA vaccines, the remapping algorithmic changes. We're doing 3 of these, the Tempest, Meshless, and adaptive remapping, and then I'll talk about clinical trials that we're running with these. So some of you are already familiar with Tempest Remap. This is Paul Ulrich's remapping package. So we have this working now within MOAB, or built on top of MOAB, so that we can actually do kind of online remapping rather than sort of offline remapping calculations that we typically do. So that's all performing at scale, high resolution. We can support irregular domains. So if your land model is using watershed domains, for example, we can handle those. Paul has recently added bounds preservation, so we're flattening the curve using clip and assured sum type algorithms, and we're looking at other property preservation techniques. So the other remapping technique we're introducing is adaptive online remapping. This is using these weighted least squares, non-oscillatory schemes, where you can adjust the order of the remapping based on properties of the field itself. So this is, you can adjust the order of the remapping for steep and smooth regions. It also is very good at dealing with kind of sharp discontinuities in the field. So we can manage those sorts of changes too. So this again is it's an online remap. It's relatively expensive, but again, we need to find ways of using this parallelism anyway. So we can use it for advanced remapping. And then finally, we're introducing some meshless remapping. As many of you know, in a lot of coupled models, you're typically exposing only one mesh representation to the coupler, whereas we'd really like to be able to remap from native staggering locations from the source and destination. So meshless allows us to do this. This is work by Paul Kubery at Sandia. And we can support now native field locations for various degrees of freedom representations. So whether it's vertex or edges or cell centers, we can actually remap from the native location. This uses a generalized moving least squares algorithm. Again, we can do global conservation and local bounds preservation, and we support a variety of degrees of accuracy. So first to fourth order basis functions. We do plan additional property preservation here too. This is particularly going to be useful for sort of vector-based remapping where we want to preserve properties of the vector field. Okay, and then I mentioned we're coming into clinical trials now, and we've got a method for kind of doing robust evaluation of all of these remapping methods, where we've developed a set of common metrics in a Python package for looking at metrics like conservation, accuracy, global and local extremer preservation, the accuracy of gradients, and those sorts of things. So it treats the remapping itself as a black box and computes these metrics. Another important piece of this is that we're using analytic representations of actual observed fields. So we've taken fields like cloud fraction or precipitation and created truncated spherical harmonic representations of those. So it's basically an analytic representation with spherical harmonic expansions. And that allows us to do accurate kind of error estimates and order of convergence. So you see the figures on the right. We've done intercomparisons for the three schemes I just mentioned, and then the ESMF remap is sort of our placebo case. So this has been done with sort of fully global grids. Now we're starting to work with meshes with topological holes or compliance with mask orders. So the ocean ice meshes always wear a mask, a land ocean mask, for example. So we're dealing with meshes like that in these intercomparisons. So the intent here is to really give a quantitative, serious intercomparison of all these. So now I'm going to switch to the time integration techniques as well, and this is going to be important not only for current couplings, but when we start breaking up these processes and trying to do time integration across a variety of time and space scales. We need to revisit how we do time integration. So we're doing a combination of both exploring new time integrators as well as doing detailed analysis of current time integration techniques for stability and consistency. So to do that, we're often dealing with sort of simpler analogs of the coupled system. So this is one example where we have kind of advection diffusion equations with a flux condition in between the two components. And we're looking at new schemes. So this is another kind of Sandia developed scheme that we call bulk interface flux recovery. And in this case, you define the interface flux as an auxiliary variable, kind of like a Lagrange multiplier, and then you use shear complement approaches to isolate those fluxes and the interface degrees of freedom. And this gives us a scheme that's actually conservative, stable, with a consistent time discretization, but it still allows the component models themselves to integrate independently with their own time discretization. So, so that's one example, and this is just a quick analytic, again, error estimate and convergence estimate. But one of the interesting things is you find out that the error really increases if you're using inconsistent time stepping schemes between surface flux calculation and the actual time integration. So then this is another example of an analog with two compressible Navier-Stokes components, where the simplification has come at the interface between the two, where we have a rigid lid boundary essentially between the two. And again, we're looking at new schemes for coupling here, where we're doing implicit explicit, where the ocean is an explicit time integrator and the atmosphere is using an implicit integrator and combining those at the interface. So again, we're just kind of early in kind of exploring these, but again, you can do some simple error and convergence tests that you see on the right, and we are able to get sort of higher order time integrations and these sorts of coupled systems. So that's just another example of the type of schemes we're looking at. So I mentioned we're also doing kind of coupling analysis of these time-stepping schemes. So both eigenvalue analyses and normal node analyses. And just as one example of an interesting result here is that with these simplified systems, you can actually develop a kind of stability constraint similar to CFL condition based on sort of the surface diffusion coefficients compared to sort of coupling parameters. So this is work by folks at Oregon, Ong Zhang and Zhengyi Liu at Ohio State. So once we have this condition, we can actually look at existing coupled systems like E3SM, look at the data sets and see how often we kind of exceed that simple condition. This doesn't necessarily mean that the simulation is unstable because that was generated for a simpler case, but it gives you kind of an idea of where you are in kind of stability regime for these simulations. And sure enough, we find that looking at the data, instability does, or this instability criterion is sort of exceeded in regions with small diffusivity and large coupling coefficients. And then in this last slide, this can both be seasonally and spatially varying. So this instability can show up in a variety of conditions. So again, the condition is for a much simpler configuration. So it doesn't mean we're unstable, but it does mean we may be close to kind of an instability regime. And we need to further develop these to see if we can come up with ways of really understanding whether our coupled simulations are stable across the integrated system. So that's kind of a quick run through of all the work we're doing under CANGA. Again, the task parallel work is progressing. And we should be able to come back next year and tell you how viable we think that is. And as I said, on paper at least, it provides us some advantages, and we'd like to see if that works out in practice. And as I mentioned before, mixed programming models are probably likely even if we do decide to go this route. And I think it's still worthwhile to continue to break up these large components, even if we're not using a full task parallel runtime. And then I went through the sort of algorithmic improvements we think we need for coupled system as well. So I think I'll stop there and we can answer questions.